In this next series of lectures, we're going to try to build up our knowledge of atoms and molecules and compounds, so that way we can better understand the different chemicals that we find inside plants like cannabis. So when we talked before about matter and how chemists like to categorize it, we talked about the difference between just pure substances and mixtures. And so this lecture is going to focus on the elements and compounds that make up just substances. We're going to leave mixtures for later when we have a much better understanding of the structure and the geometry and the way electrons are distributed in a larger molecule. So we're going to start with atoms. We're going to then build up to an understanding of compounds, and we will talk about exactly how those compounds form in the next series. So let's start with just the fundamental structure of an atom. I've got a picture of one right here. It's a kind of simplified version, like all pictures of atoms, right? So what we have structurally here in the very center is the nucleus. So it's blown up here kind of as an offset. And inside the nucleus, we have protons and we have neutrons. So our protons and neutrons have about the same mass. There's a slight difference kind of, but it rounds to be the same number. They're each 1.7 times 10 to the negative 24 grams. So it's super tiny. And that's just each proton and each neutron. So if I was going to actually write that out, and I could do it and then delete it, it would be 0. Let's see. It would be that many zeros before we actually got to the 1.7 part of the gram. So this is extremely tiny. All right, let's get rid of all those zeros. So those are its mass. In around our nucleus, we have we're going to call it a cloud, an electron cloud. It's going to be a space around the nucleus where you might find electrons. And so somewhere in here, there's like a little electron zipping around. And elements will have, or atoms will have different numbers of these. Electrons are even smaller in size than our protons and our neutrons. So their mass is 9.1 times 10 to the negative 28 grams. And so that's 10,000 times smaller than a proton or a neutron. That's really tiny. It's so much smaller than a proton or neutron that when we talk about the relative mass of electrons to the protons and neutrons in the nucleus, we say it's negligible. We're like, it has mass, it is matter, and it is so tiny compared to these other subatomic particles that we're not even going to count it and add it in when we're calculating the mass. You can, but then you end up just kind of rounding off its contribution to the overall number of its weight, its mass. Okay, so that's the relative size of these particles in terms of how much they weigh. But now let's kind of think about like how much space they take up, right? So all matter takes up space and has mass. So if we think about the overall atom, on average, we're gonna, every atom's different. Some are much smaller than others, but we could say that the amount of space that electron cloud is taking up is about 10 to the negative 10 meters. So small, but not quite as mind-boggling tiny as the mass, right? But still, that is saying that it's 0.1. That many zeros before 1 meters. So super tiny. The nucleus, though, is even smaller. So this little nucleus right here, that's actually on the order of 10 to the negative 15 meters. So where the mass of our electrons is basically a rounding error, and we call it negligible, the volume of that nucleus is essentially negligible too, compared to the size of the atom. So that's the same as a baseball stadium sized atom having a nucleus that would be smaller than a baseball itself, maybe more like a ping pong ball. So that difference is huge. So much so that we can say that the volume of an atom is really determined by the electrons, but the mass of the atom is completely determined by the nucleus, which kind of gives an interesting connection from just like one subatomic particle is really making up the whole picture of like volume, or just to make up all of its mass. The structure of the atom is going to determine entirely on the charges of these subatomic particles. And so what I mean by charge is that it has positive or negative character, or it's neutral, which means it has neither. And so this is really similar to the way magnets work in terms of the opposites, one being like we call north and one being south, or plus or minus, and that they're attracted to each other when they're opposites. And when they're the same, they're repelled. And so it's not that one is a negative one value and one is a positive one value, so much as it's a way of characterizing that they're opposites. And so our protons have a charge of +1, and our neutrons are neutral. They don't actually have a charge. They're just something with mass, so that we think of it as 0. And then our electrons have a -1 charge. And so it's really the electrons and protons that have opposite charges. And so our nucleus, which has all that mass, is comprised of particles that have charge or have no charge. And then around it, it's the opposite. So there's this thing called Coulombs Law. Right here, I have kind of a picture to help describe it. And I could write an equation for you, but I'm not gonna. Instead, what Coulomb's law tells us is that if you have two particles that have opposite charges, they're attracted to each other. And if you have two particles that have the same charge, like they're both positive or they're both negative, they repel each other. And so we see this kind of fundamental property of how charged particles behave ends up explaining most behavior in chemistry. And so we can keep coming back to this idea that opposites attract. And this will explain how we form bonds and how molecules form, and then how those molecules behave when they interact with other molecules. And it's just kind of this foundational piece. And it's weird because you're like, wow, like it comes back down to that like opposites attract sort of analogy about friendships or relationships. And it's really actually just about subatomic particles. So that's represented right here, showing that it's our opposite charges that are going to attract. So in this case, it is our electron, that's the -1, and our proton, that is the positive one. And then the neutron, having no charge, is really working on this problem of the nucleus being very tiny and these particles being right next to each other. And there's going to be this repelling effect, because if you bring two protons close right next to each other, they're going to repel each other. And so neutrons kind of create a bit of buffering, so that makes it easier for those particles to be close together. So I'd like to just kind of in the corner here draw a quick version of an example using lithium. So let's write that out. So we've got lithium. So lithium as an element has 3 protons. Let's look at an isotope of it, or we'll say it has 3 neutrons. Some lithium atoms may have more or less neutrons. We would call those differences isotopes. And it's going to have 3 electrons. So I'm going to start with the middle, where I'm going to have my 3 protons, 1, 2, and 3. And I'm going to add in my 3 neutrons. 1, I don't know, 2, 3. And that's going to represent my nucleus of the lithium atom. But that's just one part of it. The positive charge of that nucleus is going to be attracted to the electrons that are then going to spend time in the space around it, staying relatively close. And they're going to be kind of out here. And it's really hard to know where they are at any given time because they are so tiny. And it's really hard to know which direction they're going because they're so tiny. So they're just going to exist around it. And I like to think of them as like moving around so fast that it kind of like creates this cloud. And really the cloud word comes from us saying there's a probability of finding an electron in a sphere around the nucleus that is sometimes a sphere shape. Sometimes it looks more like a figure 8 instead, or a 4-leaf clover. And we call that a cloud of probability. So it's kind of a weird way to use a word that describes kind of the, condensed water in the air, but there we have it. So this is how I would represent an atom. Some people like to put a ring to represent that the electrons are kind of around the nucleus, but they're definitely not orbiting around it like planets orbit around the sun. I know that we often kind of characterize atoms that way. It's kind of got that nice atomic era old-fashionedness to it. That's fun, but really they're just kind of somewhere around that nucleus. All right, so this is our structure of an atom. We'll next dive a little bit more into defining what an element is.